Okay, let's dive into a concept in async Rust that can seem, pretty intimidating at first, but is absolutely crucial for writing safe, high-performance code. We're talking about pinning. If you've ever been brave enough to write your own future, or even just peek under the hood, you've definitely run into this signature. And that pin at mute self part, it just looks weird, right? It can be a real head-scratcher. What is it even doing there? Well, that's what we're here for. We're going to pull back the curtain on Pin and really understand why it's the secret sauce behind Rust's famous zero-cost abstractions for async programming. To really get why Pin is so important, we have to see the absolute catastrophe that happens without it. Let's look at the exact problem it was designed to prevent. So Rust's whole memory model is built on this super efficient idea. By default, values can be moved around with just a simple memory copy. For most things, this is great. It's fast, it's simple. But it has a dangerous side when we're dealing with a very specific kind of data structure that pops up all over the place in Async Rust. And why are they so common? Well, when you write a nice, clean async function, the compiler does something really clever behind the scenes. It turns your code into a state machine to keep track of where you are at every dot await. The thing is, this state machine often ends up with fields that point to other fields inside itself, and that is a self-referential struct. All right, let's watch the train wreck happen in slow motion. Here's our future, paused at an await point, just sitting in memory at, say, address 0x1000. It's got an internal pointer that's correctly pointing to its own data. Everything's fine. Now the async executor comes along and decides to move it to a new spot, 0x2000. But, look what happened. The pointer inside the struct didn't get updated. It's still pointing back to that old empty memory address. The very next time the code tries to use that pointer, boom, game over. That's undefined behavior, the scariest thing in systems programming. So how does Rust, a language that is obsessed with memory safety, stop this from ever happening? This is where our hero, Pin, finally enters the scene. Now, it's really important to get this straight. Pin isn't some new, magical kind of pointer. It's just a wrapper. Think of it like a handshake deal, a contract you make with the Rust compiler. When you wrap a pointer in Pin, you are making a solemn promise. Hey, compiler, I swear the data this thing points to will not be moved. It's just like pouring the concrete foundation for a house. Once that data is pinned, it's anchored in memory. It's not going anywhere. You can work with it, you can change it, but you can't move it. The only thing you can do is tear it down when you're completely finished with it. Okay, but you might be thinking, hold on. I'm pretty sure I've wrapped a number in Pin before, and I could still move it around. What gives? That is an excellent question. It's because of a special marker trait called unpin. Most types, like integers or strings, have this unpin label. It's basically a hall pass that tells the compiler, hey, it's totally cool to move me, I don't have any of those tricky internal pointers. Pin's strict no-move rule only kicks in for types that specifically do not have this unpin label, like our self-referential futures. All right, so let's get practical. How does this all translate into the tools and rules you'll actually use when you're writing async Rust? This little cheat sheet tells the whole story. Look, if a type is unpin, like a number, it doesn't matter if it's pinned or not. You can always move it. Pin just gets ignored. Now, look at that third row. If a type is flant unpin, like a future, and it's not pinned, you could still move it. And that's the danger zone. That's where crashes happen. The magic is all in that last row. When a flant unpin type is wrapped in pin, the compiler forbids you from moving it. And that is safety. So how do you actually pin something? You've got two main tools in your toolbox. The easiest way is heap pinning with box.pin. This just moves your future onto the heap, which gives it a stable memory address forever. Super simple, but it does cost you a tiny bit of performance for that memory allocation. The other option is stack pinning with the pin macro. This is awesome because it's totally zero cost, no allocation needed. The catch is that it's more restrictive. Your pinned data can't live longer than the current function it's in. And here is a pro tip that will save you a world of headaches. Seriously, once you've penned a struct, the compiler makes it really hard to get at the fields inside without using unsafe code. To solve this, basically the entire Rust ecosystem has standardized on a fantastic crate called Pin Project. It automatically generates all the safe boilerplate code you need to get a clean, safe API to work with the fields inside your pin structs. Okay, let's zoom out for a second. We've been deep in the weeds with pointers and memory. why does any of this really matter to you day to day? It all comes down to this. Pen is the silent guardian, the invisible anchor that lets Rust's async model be both incredibly safe and incredibly fast. It stops those memory disasters before they can ever happen by guaranteeing self-referential futures stay put. And it's that guarantee, that contract, that unlocks the compiler's zero-cost magic, letting it transform your async code into a blazing fast state machine without ever compromising on safety. So by understanding Pin, you've really grasped the fundamental physics of a Rust future, how it can safely exist in memory without blowing up. But a future on its own, it's just a blueprint. It's dormant. It needs an engine, an executor to actually pull it, to drive it forward and bring it to life. And that, well, that's a whole other story.